Welcome to the course Compiler Design. In this lecture, we are going to discuss about the second technique of bottom-up parser, which is called as LR Parser. In our previous lecture, we discussed about introduction to bottom-up parser. Then the first technique is shift-reduce parser. Now, the very important familiar LR parser is the technique of bottom-up parser. So now in this lecture, we will discuss about what is LR parser, then why LR parsers are used. Then here, some items are required to construct LR parser. So those items are called as LR0 items. Then from the items, we will construct its deterministic finite automata. So these are all the topics we are going to cover. Now let us come to the introduction about LR parser. So this is the general way of implementing handle pruning. So that is LR parser. So now here the LR will use by default the argument as K. So LRK parser will parse the input string by applying rightmost derivation in reverse. By applying rightmost derivation in reverse. The LRK parsers are bottom-up parsers that are capable of handling context-free languages very efficiently. In LRK, the L stands for left to right scanning of the input. Then the second letter R stands for constructing a rightmost derivation in reverse. Rightmost derivation means right to left substitutions, but reverse means right hand side. In place of right hand side, we can substitute the left hand side header of the production. Then K stands for the number of input symbols of look ahead. Those are all used in making parsing decisions. Like in LL1 predictive parser. So one is also, so what is this? One input symbol. Symbol of look ahead. So your first L stands for left to right scanning of the input. The second L stands for leftmost derivation. Whereas in LR parser, L stands for same left to right scanning of the input. Then R stands for rightmost derivation in reverse. Then whereas K, number of look aheads. So by default, suppose here different cases are there. If K equal to 0 or K equal to 1 are of only practical interest, and we shall consider only LR parsers with K less than or equal to 1. So here when K is omitted, then by default it is assumed to be 1. That means here K is not there. So here by default this is 1. So here always we will consider 1 as the look ahead. Compulsory one input symbol is required to take parsing decisions. In any special cases, other than 1 means they will specify, that is 0, K equal to 0. So this is the expansion of LR and K. Now why LR parsers? So LR parsers are table driven like LL1 parser, similar to predictive parser. So LR parsers are table driven much like the non-recursive LL parsers. LL means this is a predictive parser. Non-recursive. Anyway, predictive parser is nothing but non-recursive descent parser without backtracking. So these LR parsers are also similar to LL parsers, that is predictive parsers, which are table driven. A grammar for which we can construct a parsing table using one of the LR parsing method. So here we are having 3 types of LR parsing methods that we are going to cover one by one. First, SLR parser, which stands for simple LR. Second one, canonical LR parser, which is abbreviated as CLR. Then third one, LALR, which stands for look ahead LR. So these 3 types of LR parsers are there. We will discuss all these parsers one by one. Then so a grammar for which we can construct a parsing table using one of the LR parsing method, either SLR or CLR or LALR. Then it is said to be an LR grammar. So a grammar is said to be LR grammar means a parsing table is constructed by using any one of the three methods. For a grammar to be LR, it is sufficient that a left to right shift reduce parser that can be able to recognize handles of right sentential form when they appear on top of the stack. So for any grammar to be LR means it is sufficient that have a left to right shift reduce parser that can be able to recognize the handles of right sentential form when they appear on top of the stack. So these are the reasons why we have to choose LR parsers. So now there are some advantages of LR parsers. So LR parsing is attractive for a variety of reasons. The first one is LR parsers can be constructed to recognize virtually all programming language constructs for which context-free grammars can be written. So LR parsers can be constructed to recognize virtually all programming language constructs for which context-free grammars can be written for those programming language constructs. Then the second advantage, the LR parsing method is the most general, non-backtracking shift reduce parsing method. So yet it can be implemented as efficiently as other, that is more primitive shift reduce methods. So then this is the another advantage. Then coming to next advantage, an LR parser can detect a syntactic error as soon as it is possible to do so on a left to right scan of the input. Like every phase encounters errors in predictive parsers also, we discussed error recovery. So here also LR parsers can also detect a syntactic error when as soon as it is possible to scan the input from left to right. Then LR parsers can describe more languages than LL grammars. This is one of the advantages than LL parser or LL grammar. LR parsers can describe more languages than LL grammars. Then there are some drawbacks also in LR parser. So what are the drawbacks of LR parser? The main drawback of LR parser is that they consume too much time to construct by hand for a typical programming language grammar. So manually, whenever we are using LR parsers to implement a typical programming language grammar, which takes too much time for construction. But these disadvantages can be eliminated by using some of the LR Parser generators, which is called as YACC. Yet another compiler is the automatic parser generator. So like in lexical analysis also, we have lexical analyzer generator that is called as lex tool or flex tool. Like parser also, we are having automatic parser generator, which is called as YACC, and another compiler. This we will discuss end of this chapter. So now these are the advantages and disadvantages of LR parsers. Then coming to types of LR parsers. So there are mainly three types of LR parser. Just now we mentioned in bracket in the previous slide. So there are three types of LR parsers are shown below. The first one is simple LR parser, SLR. So this parser is easy to implement, hence the name simple LR. But sometimes it may fail to produce the parsing table for certain types of grammars. Then the second type is canonical LR parser, abbreviated as CLR. This is the most powerful parser than the remaining SLR and next one also. This parser is more powerful and works on very large class of grammars, but it is very expensive to implement. So canonical parser is the most LR parser. Then the third type is called as look ahead LR parser, LALR, look ahead LR parser. So this parser is intermediate in power, in computational power, lies between simple LR and CLR. So this parser is intermediate in power between SLR and CLR parsers. This parser can be implemented for most of the grammars. So these are all the three types of LR parsers. These three are very, very important. Now we will discuss one by one. First, before starting our simple LR parser, SLR parser, we needs to construct some items and DFA. So that we will call it as items and LR0 automaton. Here LR0, here you can see k equal to 0 case. So 0 look aheads here. So now how to define item? Now onwards item is also called as LR0 item. So how to define item or LR0 item? So an LR0 item or item of a grammar G is a production of G with dot operator on the right hand side of a production. So an item or LR0 item is nothing but for a given original grammar, you can add a dot operator in the right hand side of the production starting from left side. So first you can place a dot operator in the right hand side leftmost position. Then from that you can move over one symbol at a time. So then based on that you can add further new items. For example, let us consider the production A derives BCD is one production. The various items that can be obtained using this production are, so here you can see A derives BCD. As for the definition, first you can place dot in the right hand side in the leftmost. Now here dot is placed. So this is first LR0 item or item. The second one, now what you have to do, you can move dot over one symbol at a time. Now dot is moved after B. Now this will becomes B dot C D. Then next one dot is moved over next symbol towards right. Now the next item is B C dot D. Then next one is dot is moved over D. So then A derives B C D. So you can move until all the symbols are reached. So whenever the dot is moved end of the right hand side of the symbols, then you can stop. So now this we will call it as completed item. Completed item. So whenever dot is moved or placed in the right hand side rightmost, so then we can say that item is called as completed item. Then you can stop here. Till this step we have to move the dot over one symbol at a time. Now those are all called as collection of sets of LR0 items. Here you will get many sets of items. Those are all called as canonical collection of LR0 items or simply LR0 items. Now here you can see that first dot is placed in right hand side leftmost, then moved over one cell, that is over B, then over C, then over D. Now you can stop here. So this is called as completed item. So till this step you can apply for every production of the grammar to move dot over the right hand side rightmost. So now if you are having a null production, say let us see for the production of the form A derives epsilon, then the item is defined as simply A derives dot. So here null is replaced with dot only. So for null productions, the item or LR0 item is simply a dot, starting with same left hand side variable. Now finally using these items, the previously obtained items including null, so are called as canonical LR0 collection. canonical LR0 collection are simply sets of LR0 items. From these items, we can construct a deterministic finite automaton. Finally, by using this automaton, we can make parsing decisions such as shifting and reducing, shift and reduce operations. So using this DFA. Now in LR0 items, all the items are named with I, capital I, suffix with 0. Item 0, that is step, initial step. Then item 1, item 2, and so on, item n. You can take n unique sets of LR0 items. Then every item will be treated as state of a deterministic finite automaton. Then wherever we are moving a dot over the grammar symbol, that symbol may be a variable or terminal that can be treated as the transition labeled with that grammar symbol. Then it is moving to the same item or next item, like same as the automaton from a state on one input symbol, it may goes to the same state or different state, similar to that. So now, how to construct LR0 items or items, that is very important. So now the canonical LR0 collection of items for a grammar can be obtained by using the following. First, the grammar should be an augmented grammar. What is this augmented grammar? We will see. Then by using closure function, then by using GOTO function, then finally items function. Items function nothing but collection of all the items obtained. So to construct a canonical LR0 collection of items or simply LR0 items, we need the following things. First, the grammar should be augmented grammar. Then we have to use closure function. We have to use GOTO function. Then we have to use items function. Now, what is augmented grammar? We will see one by one all these. A grammar G, the standard definition equal to VTSP, be a grammar. An augmented grammar denoted as G dash for the grammar G is defined as G dash equal to V dash T S dash P dash. Except terminals remaining, all are changing in augmented grammar. Variables are changing, now named as V dash. Then starting variable is also changing, now named as S dash. Then production is also changing, named as P dash. Now where V dash is obtained by the union of V union S dash. So here whatever the start variable in the new grammar G dash. So take union of the variables in original grammar G along with this S dash. So now these are all the variables of G dash. Now P dash, the productions are obtained by using all the productions in P of G. Then you can take union of, so union of this S dash derives yes. So this is the new production. So this new production is added to P of G. Remaining all are set. So where S dash is the start symbol for the augmented grammar G dash. Whereas in original grammar G, S is the starting variable. Whereas augmented grammar G, S dash is the starting variable. Simply this is nothing but an augmented grammar consisting of a new starting variable. Then with that a production is of the form new starting variable derives the previous grammar starting variable, that is S. So then the grammar is said to be augmented grammar. So actually why we have to introduce this new production, the reason you can see here. The main purpose of the new starting production is to indicate to the parser when it should stop parsing and announce acceptance of the input. That is, acceptance occurs whenever the parser is about to reduce using the production. S dash derives yes. So the acceptance occurs whenever the parser is about to reduce using the new production, that is S dash derives yes. That is the purpose of introducing this new starting production. Then the grammar is said to be augmented grammar. So now let us see one example. So this is the given grammar. Obtain augmented grammar for the following grammar. Here E derives E plus T or T, T derives T into F or F, F derives E within parentheses or ID. So this is given grammar G. Now G dash augmented grammar. What you have to do here? S equal to E, the starting variable. Now what you have to do? Introduce another starting variable. Let us say E dash derives E. This is the only step. So remaining all are same. Then E derives E plus T or T and so on. Now this is called as augmented grammar. By introducing a new starting variable, let us say with the dash of the earlier starting variable. Earlier starting variable is E, then its new starting variable E dash. If it is S, S dash. If it is T, T dash, like that. Derives now the old starting variable in the given original grammar. E is the starting variable. Then E productions you can write that as it is. So this is called as augmented grammar. Very simple. Now here you can see. So by adding the production, E dash derives E. So then the augmented grammar is generated. Now here you can see, by adding the production, E dash derives E to the given grammar G, we get the augmented grammar G dash as shown below. E dash derives E, remaining all are same. E productions, then T productions, then F productions. So that is called as augmented grammar. First, you can check out any given grammar, whether it is augmented or not. If not, you can convert into augmented grammar by introducing a new starting variable and the production S dash derives S form. Now, once augmented grammar is obtained, then what you have to do? By using closure and GOTO functions. Then closure of item sets. Here we are having some rules. So where I is set of items for a grammar. Now onwards, item is named with capital I, suffix with item 0, 1, 2, n, like. So where if I is set of items for the grammar G, then the closure of I is constructed using the following two rules. Initially, add every item in I to closure of I. So initially, whatever the item you obtain, you can add all items to closure of I. Then after that, after adding initial item in I to closure of I, the rule 2 is of the form. If the item is of the form A derives alpha dot B beta. Here you can see dot is placed after alpha. Then after dot, a variable is there. Here you can see B is the variable. So this item is in closure of I. That means it may be I0 or I1, so on so. Then B derives gamma is a production. After dot, a variable is there. That variable contains a production. Then what you have to do? You have to add the item corresponding to the production. B derives gamma to closure of I. That is, add B derives dot gamma for the original production. Here B derives gamma is the production. Now this item means initially you can place dot in the right hand side leftmost position. So this is added to closure of I. So whenever after dot a variable is there, if that variable contains a production, then that item is by putting dot in the right hand side leftmost, that is added to closure of I. So then add B derives dot gamma to closure of I. So rule 2 is applied only whenever a dot is placed before a variable, if that variable contains a production. So then you can add that production items to the current closure value. Then this rule, apply rule 2 repeatedly until no more new items are added to closure of I. So like NFA to DFA construction in automata theory, we will start with initial state. Then from initial state, we will find the transitions on all the inputs. On any one input, if any new state is occurred, that can be considered as the next state of DFA. Again, you can find the transitions of the new state with all the input symbols. Like that, you have to continue till no more new states are occurred. In the similar fashion, the rule 2 is applied repeatedly until no more new items are added to closure of I. So that is closure function. Now let us see one example here. So now here consider the following augmented grammar. Directly augmented grammar is given. E dash derives E, then E derives E plus T, so on so. Now the first question is if I equal to the item, E dash derives dot E. So then initially E dash derives dot E is in item I. Then we have to find out closure of I. Now here you can see closure of I means E dash derives dot E. Now how to find this one? Here you can see first E dash derives dot E. Now this is in the form of alpha dot B. Beta it may be null. Don't bother about. So here it is in the form of A derives alpha dot B beta. So now B is the variable. Now E is the variable. Now E contains productions. E contains two productions. E derives E plus T or T. So you can add these productions to this closure. This closure, whatever the name, let us say, you can make it as some I naught. Add to closure of I naught. Now dot E, the E productions are E derives E plus T actually, then E derives T. But whenever you are adding a production to a closure means compulsory, you have to put dot in the left hand side, right hand side, leftmost position. So E derives dot E plus T, then E derives dot T. So again here you can see you can apply the rule 2 repeatedly. So if every item is in the form of alpha dot B beta, again here you can see alpha is null dot B, B is E. Anyway, E items are already added. Then again next one here you can see this is A derives alpha is null dot B is T and beta is null. Now here B is T. T is the variable. T contains productions. Again you can add T items here. T contains two productions. So that is first T derives dot T into F. The productions you can convert into items by putting dot in the right hand side leftmost position. So now here next production of T is T derives F, but here dot F. Now again you can see after dot a variable is there. That variable contains production. T productions are already added. Now after dot here F is there. F is the variable. F contains productions. So now you can add F items also. Now F derives, the first one is dot left parenthesis E right parenthesis. Then the seventh one is F derives dot ID. Now here you can see after dot left parenthesis is a terminal. Only if variable is occurred, then only you can apply rule 2. Then after dot ID is also a terminal. So here no variables are there. Now you can stop here. Now you can see these are all 1 to 7. These are all the items for the closure value. That is E dash derives dot E. This is closure of I. I means closure of E dash derives dot E. So like that we can find out. Similarly, the second one, F derives left parenthesis dot E right parenthesis. For this, let us check in the similar fashion we have to do. Now let us see the first one, what I explained. Same thing is shown here. Here you can see. So now the second one, let's move to the second one. So the second one is F derives, here dot is there. Dot is there before E. E is the variable. Now alpha dot B beta. So now B is E here, variable E. So you can add E items here. Now E derives, again two productions are there. Dot E plus T. Then third one E derives dot T. Again you can see after dot a variable T is there. You can add T production. T derives dot T into F. Then next T production T derives dot F. Again you can see after dot a variable F is there. Again you can add the F productions. F derives dot left parenthesis E right parenthesis. Then F derives dot ID. But here you can see here dot is the given product item. Dot is placed after left parenthesis, but here before left parenthesis. But these are all different items based on the position of the dot. Now these are all the LR0 items for the item F derives left parenthesis dot E. So like that you can find out LR0 items for every production is of the form of A derives alpha dot B beta. as per the rule 2. Repeatedly, we can apply rule 2. So like that, we can find out closer values. So then coming to whatever we discussed, the algorithm is given here. The same steps are incorporated in the algorithm. Algorithm to find closure of I. That means item. Function, let us say function closure of I. Let us say j equal to I. Repeat for each item A derives alpha dot B beta is in J. And for each production B derives gamma in G. If B derives dot gamma is not in J, the new item set, then you can add B derives dot gamma to J. Then return J, the resultant items of that closure I. So that is the simple algorithm for computing closure values. Then coming to the next function, GOTO function. So now for LR parser implementation, all these items are required. That is function closure values and GOTO values. Then coming to GOTO. So GOTO contains two arguments at two parameters. The first one is the item. Then the second one is the grammar symbol. Whereas closure contains only the production with dot. So now GOTO of I comma x is a function which accepts set of items I as the first argument and x is the grammar symbol. It can be either a terminal or non-terminal, which is the second argument. It is formally defined as shown below. If we are having an item A derives alpha dot x beta in I, then GOTO of from the item I over the grammar symbol. Here we will take the grammar symbol where dot is placed before that grammar symbol equal to, again you can find this value by using closure of A derives alpha x dot beta. Now here you can see whenever you can apply closure means dot is moved over one grammar symbol. Now dot is moved after x. Here you can see. So by applying closure, this is the resultant item we will get. So this is the GOTO value. So that means GOTO of item comma a grammar symbol means you can take the item where dot is placed before that grammar symbol initially. After applying GOTO function, then the dot is moved after the grammar symbol. The movement of dot that can be done using the closure function. So that is the GOTO function. Simply like in Automaton, on one input symbol, moving the state, it may be a current state or next state. So in the similar fashion, GOTO also. GOTO is equivalent to, this is equivalent to delta function, delta of I on x equal to again I. That is the item set, same item or new item set. So here GOTO, we'll call it as transition function. So now the algorithm to find GOTO of I comma x is shown below. The function GOTO with two arguments I comma x. If A derives alpha dot x beta is in the item I, then it returns closure of A derives alpha x dot beta. Now dot is moved over x. So here dot is moved here. So this is GOTO function algorithm. Now let us see one example here also. So consider the same grammar, augmented grammar, E dash derives E. And so now here one item is given. So I equal to E derives T dot, one item. Then another one E derives E dot plus T. Then we have to compute GOTO of I comma x. So here x means here two possibilities you can take. Here x equal to plus is there. Then but here if you can see after T dot here null is there. So let us see how to find this one. So now first E derives T dot. This is already completed item because dot is placed at the end. So we can't change this one. Then closure of GOTO of I comma T, you will get same only. E derives T dot. There is no change. You can remember this point carefully. Whenever dot is placed at the end in the right hand side, then that is the completed item. There is no change of that item. Then coming to the second one, E derives E dot plus T. Now you can apply GOTO of, let us say this item is I, comma. So after dot, what we have plus, this is the X. Now this will be equivalent to closure of, you can apply closure of E derives E plus dot T. Now this is the new item. Now dot is placed after plus. Again you can see after dot, again variable T is there. You can apply closure rule 2. Now here the resultant items are E derives E plus dot T. Then again T derives, again the T items you can add. Dot T into F, then T derives dot F. Again dot variable F is there. F derives dot E within parentheses, then F derives dot ID. Now here F items after dot terminal, left parenthesis. Then here after dot ID terminal. Here further you want extract. Now this is the GOTO of I plus value. So like that you can find GOTO values. Now here you can see. So here dot is placed after plus. Now T is present. After that T is present. So add T productions beginning with dot as shown below. T derives dot T into F. T derives dot F. Again after dot the variable F is present. Now again we have to add F items. So now you can see after dot F is present. So add F productions beginning with dot. F derives dot left parenthesis E right parenthesis. Then F derives dot ID. After dot here non-terminal is present. So stop at this point. So like that you can find out the GOTO value. Now you got clarity. Now how to find closure and how to find GOTO functions. Now finally, canonical collection of sets of LR0 items or simply set of items that can be computed using the following algorithm. Function items G dash, where C, capital C is nothing but canonical collection of sets of items, can be obtained by using closure function. Closure of the new item in the augmented grammar with the new starting variable S dash derives dot S. By applying this closure function here dot S, you can add all S items. Then any S items contains a variable after that. Again, you can add those new items like that. So repeat for each set of items I in C. So like that, you can find the set of items using the items function. Similarly, then C equal to closure of S dash derives dot S. Then here continuation of the algorithm. For each set of items in C, for each grammar symbol X, if GOTO of I comma X is not empty and not in C initially, then you have to add GOTO of I comma X to the canonical collection of items set capital C until no more sets of items are added to C, then return C. So this items function is used to list all the collection of sets of LR0 items obtained previously by using closure function and GOTO function. Now, one example problem, final problem. So in examination, you may expect this question also. This is very important. So the question will be given like this. Consider the following augmented grammar. Obtain LR0 items or compute canonical collection of sets of LR0 items. So actually they mentioned consider the following augmented grammar, but this is not augmented grammar. Why? Because new starting variable is not included here. Now let us try to solve this problem lively. So now parallelly you will also start doing this one. So here what you have to do first, augmented grammar you can find out. Augmented grammar. So G dash is obtained as shown below. By introducing new starting variable, then the production new starting variable to old starting variable. Now E dash derives E. Now E derives E plus T. You can list out all the production separately. RT, then T derives T into F, then T derives F, Then F contains two productions. So then F derives E within parentheses, then F derives ID. Now this is called as augmented grammar. So then what you have to do, the initial item. You can take the initial item by putting dot in the starting production, right hand side leftmost. Initial item, let us say I naught. So I naught equal to, first you can take E dash derives dot E. So this is the initial item. Now here you can see after dot, we have a variable as per rule 2 of closure function. So here variable is there. This is alpha dot B beta form. Now add B items. That means E productions by putting dot in the left side of the right hand side production. Now for E we are having two productions. E derives dot E plus T, then E derives dot T. Again you can see the new items also you can apply rule 2. Here let us see. Again here after dot variable E items already added. Next item dot T. After dot T is the variable. T is the new. So these items are not there already in I naught. So you can add. T derives dot T into F by putting dot in the left side of the right hand side production. Then T derives dot F. Again you can see after dot T is there. Already T items are added. Next item after dot F is there. F is the variable. So F items are already not included. So you can add. Now F derives dot E within parentheses, then F derives dot ID. Now here you can see after dot terminal is there. Here also after dot ID is there. Further, no new items are added. Now you can stop here. This is called as item 0. Next item 1, what you have to do? You can apply GOTO function. GOTO of from I naught. You can move dot over all the grammar symbols including terminals. So now here GOTO of I naught comma X. Here X equal to what are the symbols possible to move dot over this symbol. See first item is dot E. So you can move over E only one step at a time. Then here T we can move over T also. Then here F we can move over F also. Then here we can move over left parenthesis. Then here we can move over ID also. So you can apply GOTO of I naught on X for each and every grammar symbol wherever dot is placed before that grammar symbol. That grammar symbol is either a terminal or variable. Now one by one you can take. Now every time over one grammar symbol, that item will be named as the next item. Now here I naught on E first. So you can find out I naught on E. That means in the right hand side, in I naught, wherever the items are there, dot is placed before E. Now you can move dot over E. That is after right side of the E. Now here dot E, one is there, then dot E plus T. So these two comes under this GOTO of I naught on E. Now this will becomes E dash derives E dot. Now dot is moved here. By applying this can be applied again by using closure of E dash derives here you will get E dot comma E dash derives E dot plus T. By applying closure to these two items. Why? Because after moving dot over E, these are all the new items we will obtain. Now here next one is E derives E dot plus T. Now here you can see dot is placed at the end. Here no new items are added. Now no new items. Here you can see after dot terminal is there. Here also no new items are there. These are all the items 1. Then next you can make it as items 2. Then you can take GOTO of I naught on next symbol where dot is possible to move over the symbol. Next symbol is T. Over T means here we have dot T. Only you can see the right hand side wherever dot is there before T. Dot T, here dot T into F. Now dot moves after T. Then the new items are, now here you can see. Now here you will get E derives T dot. Now T derives dot t now becomes t dot star f. Now you can see dot is placed at the end, no new items. Here after dot terminal is there, here also no new items. These are all the GOTO of I naught on t. Then coming to next one, f. GOTO on I naught on f. So before f, where dot is there, only one item, t derives dot f. So now the new item becomes f dot, t derives f dot. So now GOTO of next one is GOTO of I naught on f equal to, here you will get t derives f dot. So only one item you will get here, where dot is placed before f. Then coming to next terminal, left parenthesis and id. So next item, name it as I4. GOTO of I naught on left parenthesis. You can find out where dot is placed before left parenthesis. So now the dot is moved after that left parenthesis. Now here you can see only one item we are having. Dot is placed before left parenthesis. Now it moves to right side of that left parenthesis. Now the new items becomes, here you can see f derives. Now dot is moved after left parenthesis. Dot e. Now again you can see, so whenever dot is moved to over one symbol, after dot again any variable is there, you can apply the closure rule too. Repeatedly you can apply that rule till no more new items are added. Now here dot e is the variable, so you can add e items here. E derives dot e plus t, then e derives dot t. Again here you can see dot after dot e items are already added. Then after dot t, now t items are not there in I4. You can add t items. T derives dot t into f, then no, t derives dot f. Again after dot t variable, t product items are already added. Then after dot f is there. F is the variable. Now add f items here. F items are not there here. Now f derives dot left parenthesis, e right parenthesis, then f derives dot id. Now after dot terminal is present. Here after dot id terminal is present. Here no more items are added. Now you can see over left parenthesis is over from I naught. Now we are all finding the GOTO value by using I naught only. Like further you can apply same for I1, same for I2 and so on. Wherever incomplete item is there, you can apply the same until no more new items are there. Next I5, from I naught, GOTO of I naught on terminal ID. So where dot is placed here in the I naught, f derives dot id is there. By taking this one, dot moves to the end. Now the resultant item is f derives id dot. See after dot nothing will be there. Dot moves to the end. Now you can stop here. So from I naught now all items are constructed. So then coming to I1 also, like that you have to proceed. Now coming to I1, wherever incomplete items are there, you can apply same. Now here this is completed item. Now from I1 over plus there is possibility. Now dot moves after plus. So now that you can make it as the next continuation item. Now I1 GOTO of I1 on plus. So let us say this is I6 item. Now GOTO of I1 on plus. Here take the production E derives E dot plus T. Now dot moves after plus. Now this will becomes E derives E plus dot T. Again see after dot variable is there. You can add initial T items by putting dot. Dot T into F. Then again dot F. After dot T variable, T productions are already added. After dot F, F productions are not there. Now you can add F items here. Now F derives dot E within parenthesis, then F derives dot ID. Now after dot terminal is there, left parenthesis, after dot terminal ID is there. Further here, no more new items are there. Now from I1 on plus, only one possibility is there. So then coming to I2, so I2 also we are having possibilities over star. So now here over star means dot moves after star. Now GOTO of I2 on star. Now that is the next item. So like that you have to proceed until no more new items are there. GOTO of I2 on star. Here the production is T derives T dot star F. Now dot moves after star. Now this will becomes T derives T star dot F. Again after dot F is there. Now add F items. F derives dot E within parenthesis. Then F derives dot ID. So from I2 only one possibility is there. Then coming to like that you can proceed. Now I3 is completed item. Here we can't proceed further. This is completed item. Then similarly coming to I4. I4 here, what are the possibilities here? We have GOTO of I4 on E. Here over E is there. Then GOTO of from I4 on T is also there. This one. Then GOTO of, you may get later some repeated items. Then I4 on F also we will get. Then here GOTO of, again here see over left parenthesis also we will get. I4 on left parenthesis. Then GOTO of I4 on ID. So find out all these values in the similar fashion. Then coming to I5, this is a completed item. Then coming to I6. So here I6 you will get GOTO of I6 on T, here dot is there before T, then F also. So GOTO of I6 on F, then over left parenthesis and over ID also. GOTO of I6 on left parenthesis, then GOTO of I6 on ID. So you can find out all these values. Similarly from I7, so here over F is possible. GOTO of I7 on F is there. Then here over left parenthesis also. GOTO of I7 on left parenthesis. Then GOTO of I7 on ID. So here sometimes you will get the repeated items, then you can give the same number. So again with this new GOTO functions, you may get some other new items. Like that you have to proceed till no more new items are there. Okay, now we will continue same in the next class also. All of you parallelly try to complete this one till this, the remaining GOTO function values also. Okay, now I stop here.